In the previous meeting, we have studied about the electromagnetic induction, especially for the topic of Faraday's law and Lenz's law. And for today's meeting, I would like to continue to the next topic on electromagnetic induction, which is the topic about inductance. There are two kinds of inductance. There are two types of inductance. So the first one that I would like to explain here is the mutual inductance. So how can we describe mutual inductance? So you can see in this slide, we have first coils. This one, first coils carrying current I1, and let's say that this first coil has N1 turns or N1 loops, and I have another coil. We call the second coil as coil 2, and in coil 2 there is no steady current here, so we can say that I2 is equal to 0. Let's say that coil 2 has N2 turns or N2 loops. From the previous meeting, you already know the concept of Faraday's law. The concept of Faraday's law is that we can obtain the induced EMF because there is a changing of flux per unit time. So if coil 1 has a steady current I1, and we know that the magnetic field can be induced from the conducting wire here. If the I1 constant, so there will be no change of the magnetic field. So the magnetic field is also constant. So it means that if coil 1 producing magnetic field B and the value of B here is constant, so it means there is no induced EMF in coil 2. Then what do we need to obtain the change of the magnetic field? So it means that I1 here must be changed by time. So I1 must be in a function of time. So if I1 changed by time, we can obtain the change of the magnetic field every second. And the changing of the magnetic field can produce the changing of the magnetic flux penetrating coil 2. And then we can obtain the induced EMF in coil 2. So that's the main or basic concept of the mutual inductance. So based on the Faraday's law, we know that the induced EMF can be calculated using this formulation. So if I want to calculate the induced EMF in coil 2, so here is E epsilon 2 is equal to minus N2 d flux B21 over dt. So flux B21 means the flux penetrating coil 2 due to coil 1. So then we can obtain that the flux here, we can understand that with the higher the current, the higher the magnetic flux as well. So we can obtain the relation between flux and also current. So flux is equal to K times I, sorry. So flux is K times I. K here is a constanta. So if we substitute the flux here with the value of K times I, we can obtain that the epsilon 2 or induced EMF in coil 2 is equal to minus N2 dk1 I1 over dt. And by then we can remove the K1 from the differentiation because this is constant, and then we have epsilon 2 is equal to minus N2 K1 di1 over dt. So let's make a new coefficient. So here n times k, n2 times k1, we call this as M21. So M21, this is the mutual inductance. So the mutual inductance here is a coefficient, and if we then want to calculate the epsilon 2, because N2K1 is M21, so the mutual induction in coil 2 due to coil 1 times di1 over dt. So from here we can obtain the induced EMF in coil 2 due to coil 1. And how to calculate the value of the coefficient of mutual inductance? So here we have that M21 is N2K1, and we have K1 is magnetic flux B21 over I1. So if we substitute the value of K1 to this formulation, then we can have that the M21 is equal to N2 times flux B21 over I1. So here we can obtain the value of the induced EMF and also the mutual inductance. And the second type of inductance is self-inductance. So in case of this self-inductance, let's say here we have a solenoid and we connect to the source of voltage, and there is a current passing through this loop, and the currents change by time, or there is a time varying current. And we know that this current can generate magnetic field. Because of that, we can see that because the current changing by time, and it means that the magnetic field also changing by time. So because of the changing of the magnetic field, we can obtain the changing of magnetic flux. So here we can find how is the induced EMF due to the changing of the magnetic flux by time. So the induced EMF is equal to minus n d flux over dt from the Faraday's law. And we know that flux here is proportional to K times I. And we have here, if we remove K outside the differentiation, we have nk di over dt. And let's say that nk here is equal to L. So from here, from the self-inductance, we can find that the induced EMF in case of self-inductance is equal to minus L di over dt. And L here is equal to N flux over I. The unit of L is Henry, or you can also write down the unit of L is 1 Tesla meter square of over A. We call this L as a self-inductance or just inductance. So if you find this symbol in a circuit, so this kind of symbol, we call this as inductor. So inductor is also a kind of electromagnetic properties, sorry, electric properties, I mean, just the same like resistor and capacitor. Inductor has a function to keep the energy of magnetic field. And we also have a term we call as inductance or L. Just I explained that L here is the ability of inductor to keep the energy of magnetic field. It's the same with like a capacitance or resistance. So from this explanation, you can now able to explain one other kind of electric properties, which is inductance. So how to calculate energy of inductor? So here, if I have a circuit like this, consists of inductor and also resistor, we can calculate the potential difference AB is for the inductor, the potential difference is L di over dt. So from here, L di over dt, and we know that the potential difference of resistor is I times R. If we want to find the power of circuit, so P is IV. So if we multiply by I, we can obtain here for the inductor. So for energy itself, we can find that the energy is equal to P dt. If P is IL di over dt for inductor times di, then we can obtain that the energy of inductor is equal to Li square over 2.